Hello all, welcome to the new lecture of integral equations. In this lecture we will discuss the section 3.6, that is Fredholm equations with the separable kernels. So as the name indicates, we will first define what are separable kernels, and if the kernel is separable, how we can solve or find the solution of Fredholm integral equations with the separable kernels, that we are going to discuss in this lecture. So first of all, definition of separable kernels. A kernel of the form k of x theta is said to be separable if it can be expressed as the sum of finite number of terms, each term is the product of a function of x alone and a function of theta alone. So kernel x theta is said to be separable if it can be expressed as a sum of a finite number of terms, each of which is the product of a function of x alone and a function of theta alone. Such a kernel is thus expressible in the form, or mathematically such a kernel can be expressed as k of x theta is equal to summation k varies from 1 to some fixed finite number, let it be capital N, then 1 to n fn of x into gn of theta, where fn of x is a function of x alone and gn of theta is that means gn's are the function in theta alone. So k of x theta, the kernel, is the finite sum of these products. So such a kernel is called a separable kernel. For example, any polynomial in x and theta is of this type. And another example, if we consider k of x theta as sine of x plus theta, when we look at the sine of x plus theta, we may think that this is not separable, but we can write sine of x plus theta as the sum of products of function of x alone and function of theta alone. Use the expansion of a sine of x plus theta in the form sine of a plus b. Sine of a plus b as a and b as angles. We know that sine a, the expanded function or the identity is sine a cos b plus cos a sine b. So using that, we have sine of x plus theta is equal to sine x into cos theta plus cos x into sine theta. Therefore, when k of x theta is equal to sine of x plus theta, this kernel is a separable kernel. So if the Predom equation has a separable kernel, then it is very easy to solve the equations rather than in solving it in direct method. So if the kernel is separable, then it is very easy to find the solution of this Predom integral equations that we are going to discuss now. So we are considering the Predom integral equation of the second kind. Second kind means the coefficient function alpha x of y of x is equal to 1. So the general form of the Predom integral equation of the second type is, or second kind is, y of x is equal to lambda integral a to b k of x theta y theta d theta plus f of x, where, and suppose that k of x theta is a separable kernel. So since the kernel is separable, it is of the form summation n equal to 1 to capital N fn of x into gn of theta. Therefore, y of x is equal to, we are substituting k of x theta in equation number 1. So we have lambda into integral a to b summation n varies from 1 to n fn of x gn of theta into y theta d theta plus capital F of x. Now the variable of integration is theta. So we can take the summation n equal to 1 to n fn of x outside the integral, and bring the integral into inside. So we have lambda into summation n equal to 1 to n fn of x into integral a to b gn of theta y theta d theta plus f of x. Put the equation as number 2. And we know that the integral multiplied with fn of x is a constant actually, isn't it? Even though we don't know about what the constant is unknown, but the this integral will be a constant. So we will denote this by another some constants cn. Okay. So it is seen that the coefficients of f1 of x, f2 of x, etc., fn of x. What will be the coefficient of f1 of x? When we expand the sum, we will have lambda into first term will be f1 of x into integral a to b g1 of theta y theta d theta, and integral a to b g1 of theta y theta d theta will be some constant which is unknown. So coefficient of f1 is this one. So although all these values are unknown, but we take this, we represent this as some other constants by Cn. So Cn is, we take Cn as integral a to b gn of x into y of x dx. Since theta is the dummy variable, we can use any variable inside the integral under the um, definite integral. So the dummy variable, if we take it as x, we have cn is equal to integral a to b gn of x into y of x dx. That is c1 is integral a to b g1 of x y of x dx. c2 is x integral a to b g2 of x y of x dx, etc. C capital N cn is equal to integral a to b g capital N x y of x dx. So we will get n constants. Then if these constants are known, then the solution will be, or the equation 2 will become y of x is equal to f of x plus lambda into summation n varies from 1 to n fn of x into this integral, that is cn. So cn into fn of x. So equation number 4 will constitute the solution of the Fredholm integral equation whenever these Cn's are determined. So if we know the Cn's, then we can have directly by equation number 4, we have the solution of the Fredholm integral equation in the form equation number 1. So the solution of the Predom integral equation with a separable kernel will be in this form: y of x is equal to f of x plus lambda summation n equal to 1 to n.